Hello, mic check. Sound happening. I can turn on. So it's off. Hello, mic check. Hello.
So this title is 3 words, and it's huge 3 words actually. Well, the first 2 words are okay connected, but the third word is for the thermodynamics the best best place to have discussion on. And small story, and you can keep it general a little bit for the initial part, so that that so that because there are people from chemistry and biology also. Yeah, thank you. You can take a seat right now. I will have to say something. Yes, math is math is yes. Math and computer. That's field of mathematics. This is natural science. Yeah, it's kind of only here. Always it is there in natural sciences. I don't know. Applied math could be natural sciences, I understand. Yeah, in my university. Okay. Math is part of it. Okay. Maybe it is a traditional thing from this. Some mathematicians really wanted to keep themselves separate. I'm doing things. But I deal with a lot of physics. I do a lot of nonlinear spectroscopy with optics. Yeah, my experience is that many chemists don't come with our most president. Especially those working on physical. Right. They're experts. Well, maybe on systems that are very strongly coupled to the bar, they're experts. Because we have to think of the system logic. So this guy has made his son write a paper. Really? He's already a first a single author paper. He has a single author in class. When did he write? What? Oh yeah. What happens to the beauty study? Yeah. I didn't have to get well, I didn't go to the US. The France didn't get it. Oh. Right body image. Oh yeah, yeah. We get better feeling on physics. Very often for your specialty for I think except in the gym. Yeah, try to speak differently. Okay. I think this is young. I'm going to
While replacement course coordinator, I just say I'll stand in for you, next 2 weeks.
Okay.
I thought we'll discuss later. No, so yeah, I have so I could okay.
Okay.
I welcome back all of you for this edition of the Wednesday Colloquium. And today we are really sort of happy to have Professor Seok Kim from the Seoul National University in Korea and hosted by Professor Shiraz Minwala. But before we start the formal introduction for Professor Kim, I just wanted to give you a few words of the colloquium. So, Professor Kim, this has been an age-old tradition for us ever since the founding director, Professor Homi Bhabha, started this idea of having all the natural science faculty members get together, listen to an expert in any of the branches of physics, chemistry, and biology. So, this has been a tradition, and it has also been a training ground for many students, and also, cross collaborative discussions within the institute. So, thank you for being part of this tradition and giving us your take on black hole entropy. With that, I would like to have Shiraz introduce you. So, yeah.
Okay, so Seok is an old friend of India and especially TIFR. Today he was telling us that this is his 7th visit to TIFR. Okay, Seok was an undergraduate and then a PhD student at Seoul National University. He then went on to do a postdoc at KIAS in Korea, then another postdoc at Imperial College, and then went back to Seoul National University, couldn't stay away, to become a professor, to be a professor there, and he has been there since. Seok has done many important things through his career. Perhaps several of the most important have to do with counting of supersymmetric states and black holes. So Seok in particular has been able to count supersymmetric indices and thereby count the number of states that supersymmetric black holes that make up the entropy of supersymmetric black holes in very efficient and unexpected ways that other people were not able to do. I was one of the other people. I tried. It didn't work. Seok managed to do it. Okay. And today he's going to tell us about black hole entropy, and I'm sure he'll touch on his own work.
Yeah. Thank you very much for the introduction, Shiraz. I'm so happy to, and I'm very much honored to have a chance to talk about this topic of black hole at TIFR. As Shiraz told me, as Shiraz told you, I visited here many times. The first time I visited here was when I was doing my first postdoc at my 20s, very young. And I was basically motivated to come here to learn the topic of black holes, gravity, and string theory from many of the experts at this TIFR. So basically, I learned about this topic starting from here. Based on what I learned here, I made a modest contribution to the topic. So I'm not really going to talk about the technical things I've done. I'm going to talk to you about the background. Hopefully, a small and cute story about the black holes. Hope to make it consistent surrounding the important function called entropy that the black hole carries. Okay, so let's start. The black holes are a particular class of solutions of the beautiful equation that has been figured out by Albert Einstein. It's called general relativity. And that's supposed to be, that equation is supposed to be governing the force called gravity in our world. So these black hole solutions are first found more than 100 years ago. But due to many exotic and unacceptable properties people thought that these solutions carry, they have been largely ignored, by many people. Some of the exotic properties that the black holes carry include some singularities in the space-time describing these black holes, a strange object called event horizon, and so on. So due to these strange properties at that time, people thought for a long while they still stayed in the purely theoretical territory. People have been thinking that these exceptional solutions are just mathematical artifacts of the equations rather than being relevant to our nature. Okay? The situation gradually changed, I understand, from the mid-20th century when people felt that they saw the signs of the existence of the black hole from the sky and the universe. Okay? Until these days, when we feel that from these beautiful photos, we feel that we almost see the black holes in the sky. Okay? So the object itself these days, the black hole object itself, are by now somewhat familiar to many people, not just the experts, because we hear about black holes very often in the news and so on. So the object themselves look somewhat familiar to many people, but their concepts still are not quite.
So I'm going to talk about some of these conceptual mysteries that the black holes are carrying all the way from more than 100 years ago, and try to explain to you that some of the peculiar aspects are deeply connected to some of the fundamental laws of nature that we are still struggling to better understand, especially surrounding the laws of gravity in the quantum mechanical regime. Okay? So in particular, I'm going to talk about the properties of the black holes having to do with the existence of a strange object called event horizon. Okay, so it's a surface surrounding the black holes. Okay, and the horizon, the notion of a horizon is obvious. It's a surface or a line beyond which you cannot see. Okay, so if an observer stays out of a black hole, there's a surface surrounding it so that the observer outside the black hole cannot see anything inside this event horizon. Okay, and the reason why that happens is quite clear. I mean, by now quite clear. The gravity given by the black hole, gravitational attraction given by the black hole on any events like the particles and lights, which wants to escape out of this black hole towards the outside, the gravity exerts a too strong attractive force into it so that anything that wants to escape out of it gets bended back to the black hole if it stays inside the event horizon. Okay? So apparently the outside observers cannot see inside the event horizon, and that brings an apparent lack of certain information, namely about the lack of information of the matters which collapsed to form the black holes. So the lack of information from the outside observers caused various information-related phenomena. Sometimes it's a phenomena, sometimes it causes a paradox, sometimes it poses interesting questions. So I'm going to talk about some of these information-related properties that a black hole is supposed to carry, in particular focusing on what's called the thermodynamics of the entropy, characterized by this entropy, which I'll explain. And I'll be discussing to you what these information-related properties are exhibited by black hole seem to teach us about the fundamental pictures of gravity and our nature. Okay. So let us, before discussing about this information and thermodynamics of black hole, let us step back a while and think about the situation in a more general perspective. Suppose that we are interested in describing very big macroscopic system. For instance, a tank of molecules a tank of gas consisting of many atoms or molecules. Okay? If you know all the motions and the velocities of these molecules, large Avogadro number of them, you'll be able to, in principle, determine the phenomena of all these macroscopic systems precisely. But often we are not given that many information. Often you're just given a limited number of information given by the total energy carried by this gas, maybe the volume of the tank, total number of particles there in the system, but you're not given many information. Okay? And there's a discipline in physics called thermodynamics, which tells you how to efficiently extract out a limited kind of physics out of this limited data you have. Okay? This discipline is called thermodynamics, which has been developed from 19th century, I guess. And physicists have extracted, I mean, have been studying the structure of this thermodynamics, and one master quantity which determines the property of this thermodynamic property of the system is called entropy. Okay? So this will be my key observable and key function of my interest today. So I'm going to explain to you how physicists understand entropy. Okay? So conceptually, entropy is can be defined. I'll be basically defining to you the thermodynamic entropy of this various system, but the entropy in general can be phrased to be our ignorance on the system, given the limited amount of information. You don't know the full information about these atoms, but you only know a handful set of physical quantities. Okay? If you have been knowing the complete set of information about the system, let's say if we information about the system, there will be essentially one state of the system that is compatible with all the information that you know. But since you are lacking many of the information, there are many number of states, many number of the possible states carried by this system tank of gas, which is compatible with a small number of information that you have about that. And the more the states that can be possibly compatible with the limited data you know, the more the ignorance your ignorance becomes about this system. So the number of possible states, and I'm secretly saying when I say states, or quantum mechanical state in a sense, the number of possible states of the system with limited number of information given to you is roughly called the entropy of the system. And it measures how ignorant we are, how much ignorant we are about the system. For technical reason, we take the law, but this is basically the definition of the entropy. And for thermodynamics, it plays a very, very important role. We can call it a master function of thermodynamics. Many useful thermodynamic quantities like temperatures or heat can be understood as a small variation or derivative of the entropy in various situations. Okay, so we go back to, with this understood, we go back to the studies of black holes. So black holes, I told you, has an intrinsic, outside observer, has an intrinsic lack of information about this object. So one might expect it's not too strange that black holes are also behaving thermodynamically in a sense. We can make a thermodynamic approach to understand the black holes with limited information of that object given. It turns out to be true, black holes are behaving thermodynamically in a sense. The surprising part is that the thermodynamics on this black hole is realized in a geometric manner. Okay? So the geometry is an essential part of the Einstein's general theory of relativity itself. Surprisingly, the thermodynamics of black hole is also realized in a geometric way. Most importantly, in the sense that the entropy carried by the black hole, the ignorance of the outside observer about this object seems to be encoded in the area of this event horizon surface. Okay? So there are many signs of this statement that the entropy carried by this black hole, the possible number of states that the black hole can be representing, could be encoded in the area of the event horizon. It's a geometry, right? So people have found many signs of that. And one important thing is that if you identify the area of the event horizon as the entropy that the black hole carries, it seems to obey, at least formally, many rules that the entropy in thermodynamics is supposed to obey. So thermodynamics has listed various laws of thermodynamics, and most important is what is called the second law of thermodynamics, which basically says that the entropy, as time goes on, never decreases. It may increase, but it never decreases. Okay? So it has to do with the irreversibility of this macroscopic system's evolution, and so on. So using general relativity, I think it's Hawking who has been shown that the area of the event horizon never decreases in time. So it formally behaves like the entropy. So it's showing the right behavior. And more physical argument by Bekenstein and an ingenious calculation by Stephen Hawking that the black hole should make a tiny little thermal radiation has established a precise relation between the event horizon area and the Bekenstein, the so-called Bekenstein-Hawking entropy that the black hole should carry, where the proportionality coefficients are given by a combination of fundamental constants of nature, like speed of light, Newton constant measuring the strength of the gravity force, Planck constant, which governs the quantum mechanical scales, and so on. Okay? So there were many signs, somewhat indirect signs, that the black hole should carry the entropy, given by the area of the event horizon, and there is a sign that this measures our ignorance about the possible number of states that black holes could be representing. So I'm going to talk about this simple function, the area of event horizon, and what kind of rich physics it exhibits towards a better understanding of nature. But maybe before proceeding, I'd like to emphasize this entropy is quite an abstract quantity. So I'd like to emphasize certain aspects of it before proceeding. So entropy is a very subtle quantity and very subtle notion in various ways. The first property of entropy is that if you, at least in thermodynamics, if you want to describe it properly, we have to define it using quantum mechanics. Okay, so I defined it to be the number of possible states at the fixed data that whose information you have. So counting states one by one, precisely speaking, a quantum mechanical notion. Okay, so it's nothing mysterious, but all I wanted to say is that if you study this function entropy carefully, you're gonna often get a useful insight on the quantum mechanics of the underlying system. Another funny property is that, unlike other physical observables, it doesn't measure a definite phenomenon. It's rather just measuring the possibilities rather than a definite phenomenon. In other words, it's another way of saying that it measures our ignorance. So it's, in a way, it's a very theoretical and abstract object, but it played practically very important roles of governing making us better understand the structure of the other thermodynamic observable, but that entropy itself is a very abstract quantity, one can say. Somewhat ironically, such an abstract theoretical object has been playing a very important key testing roles for the quantum theory of gravity to successfully understand the underlying structures of this Becken-Schnorking or entropy given by the area. And I can say this in the two different ways, two reverse ways. First of all, I mean, along with the development of string theory as a quantum theory of gravity, people got to use the quantum mechanical rules known for this the gravitational theory in the quantum mechanical regime, and to honestly count the quantum states of this black hole system. Okay, so doing this honest counting of the quantum mechanical system with given energies and so on, one could explain that this counting of quantum states successfully reproduces the geometric entropy given by the Becken-Schnorking law. Okay. So this is generally regarded as one of the triumphs of string theory as a quantum theory of gravity, at least in the theoretical regime, because it's explaining a mysterious geometric entropy using the more familiar notion of entropy in thermodynamics. Reversing the direction a little bit, I mean, with all these successful checks that's been made, one can take the geometric black hole entropy and regard it as counting certain states, perhaps counting states of the matter lurking behind the event horizon of the black hole, and try to get hints towards the fundamental laws of these matters, I mean, including gravity and everything. Okay? Second will be my basic attitude today. Okay? Use this black hole entropy function and try to extract out maximal interesting lessons about the laws of nature and so on. So let us get to the studies of the detailed property of the black holes, its thermodynamic property, the property of its entropy. For instance, we study the simplest black hole. It's called the Schwarzschild black hole. It's just a black hole carrying mass, and it's embedded in a infinitely large non-compact space-time called Minkowski space-time. And as a thermodynamic system, a strange property that is expected to be carried by this black hole, that is that it has a negative specific heat. Specific heat is the rate of change of the energy if you change the temperature. So if the specific heat is positive, you provide energy to the system and heat it up. You take the energy back and cool it down. Okay? If the specific heat is negative, you put energy into the system to make it colder. Okay? So it's a bit counterintuitive, but such situation sometimes happens. And it turns out that it happens for the black holes also. Okay? So this was the very famous theoretical calculation by Stephen Hawking. And he has been finding that the black hole has a temperature called TH, Hawking temperature, which is inversely proportional to the black hole mass. Okay? And here, when I say mass, we are all in the regime of Einstein's relativity. So the mass always means a contribution to the energy, according to the famous formula, E equals to mc squared. Okay? So any mass has a rest mass energy. So we can regard this relation, inversely proportionality relation between the temperature and the mass, as the relation between the energy black hole carries and the temperature. So since they are inversely proportional, obviously specific heat is negative. Big black holes are colder, small black holes are possibly hotter. Okay? And you can view this fact from the entropy viewpoint. This will be basically the only place I use a formula, but you know, I told you that entropy is basically giving you all the other thermodynamic quantities, and that includes the temperature. And if you take a derivative entropy with energy, it is inverse temperature. It's the rule of thermodynamics. And the fact that this inverse temperature is given by the mass means that the entropy, being a quadratically increasing function, is giving you this negative specific heat. Okay? Entropy is growing. It's growing fast as a quadratic function as energy goes. Okay? This is a more general fact. You know? I give an example with a particular system where temperature and energy is exactly inversely proportional, but one can generally show from this formula that if the entropy is generally an increasing function of energy, often, if it's increasing in such a way that both the first and second derivatives are positive, if it increases in a convex way, the specific heat is negative due to this formula. Okay, so you might think that entropy is a fastly growing function as the energy grows, but in most systems that you're familiar with, entropy grows concavely. Okay, its increase slows down if you get to higher and higher energies to have positive specific heat. Black holes have a funny feature that its entropy is convexly growing, leading to a negative specific heat. Okay, and the first half of my talk will be revolving around this simple mathematical fact. and the deep physics that it implies about the gravitational physics. Okay, any questions so far? Negative specific, yeah, the energy is radiated and it becomes hot, and I mean, there can be, yeah, there can be, I mean, depending on situation, there can be various explanations. Like, I'm getting to one example. I mean, I'm gonna explain why it happens in a simple case, and then get to a more deeper question of why that happens for the black holes. Okay. What's this again? Yeah. Any specific? So the black holes that I explained to you are following this this lower curve. The task of this talk will be getting a better understanding of that from a fundamental level. Okay. Yeah. Yes. So let's say in an equilibrium process, entropy change multiplied by temperature is leading to the heat, right? So yes. That first law has been also established to be holding alongside the second law. I just showed the most dramatic law that should be obeyed, but the first law is also obeyed by the Beckett-Trunking area. Yes. There was one. All right. So let me discuss about this convex growth of entropy, which is related to negative specific heat. That's not very common because normally in most systems around us, I mean, we have to heat the system to make it hotter, not the other way around. But it occasionally, occasionally can happen in some cases. I mean, if your research discipline really uses thermodynamics extensively, you might have one or two favorite examples of yours which exhibits this behavior. Whenever I give this talk, some people in the audience say there's one more example and one more so on. So, but perhaps the most well-known example among among physicists is the following. It often happens in a range of energy due to the interactions of the constituent matters. Okay, so one well-known example that I know of is a star evolving, and at some point of the star evolution, it emits energy, shrinks, but it gets hotter. Okay, so it's emitting energy and getting hotter means that the specific heat of a star is negative at some point. And that's due to a particular property of the gravitation interaction. The interactions are rearranging the total energy between the potential and kinetic energy so that the total energy may decrease, but the kinetic energy can increase. Okay? And the increase of kinetic energy is directly related to the increase of temperature. So that if you compare that with the net energy, specific heat may look negative. It's a funny act of the interactions that arranges energies into different types. Okay? So the interaction can be one cause of this phenomenon. There's another cause where entropy can grow faster and faster as you move to high energy regime. That's by the appearance of an intrinsically new state, keep appearing as you increase the energy. By that I mean, for instance, suppose that you have a particle of very high mass. No. At low energy, it's hard to generate them, to create them. So at low energy, they don't participate in the entropy. Okay? But as the energy increases, so that the energy is passing through the rest energy contribution of this mass, these massive particles can suddenly participate in the entropy, contributing to the faster growth of entropy. So if there happens a sequence of massive particles, which keeps appearing as the energy increases, this can boost up the entropy growth, making this kind of convex growth possible. And that turns out to be what happens in the quantum gravity model given by string theory, when many string theories accounted for this convexly growing black hole entropy. So I'll review a little bit of that, hopefully in a non-technical term as much as possible. Okay. So possibly I mentioned two causes of this strange phenomena, interactions and more states appearing. Okay. So let us start to investigate simple examples one by one before getting into these gravitational systems, quantum gravity, whatever. We first discussed the situation in particle physics. Okay, without gravity, such a convex growth of entropy is I don't really know of a fundamental example showing that. So let us think about simple examples one by one. For instance, we consider free particles, non-interacting ones. I first consider so-called non-relativistic particles. It's a difficult name of saying that the speed of the relevant particle, let's say the gas in the tank, the speed in the particles are much smaller than the light velocity, so that we can ignore relativity effect. The entropy formula for the non-relativistic ideal gas can be computed, or you can open a thermodynamics book, and the famous formula is this. It's very well known to scale like log of the energy. Log function is an extremely slowly growing function, which is concave. And the reason why the reason why you get this slow growth is the following thing. So in the non-relativistic ideal gas, normally the particle number is fixed. You have no enough energy to create or annihilate these particles. So with fixed particle number, entropy increases in energy as by having larger number of states at larger energy for a fixed number of particles. Okay? Physicists say that if you go to larger energy, the fixed number of particles have larger volume in the phase space or so on. But anyway, the message is that the particle number is fixed. The kinematics, the motions, allow for more states if you have a larger energy. And the structure of this kind of increase of energy is extremely slow, log or something. Now we go to a little bit more interesting case. We call it relativistic particles. It's particles moving as fast as the light speed. We consider a case of very high energy so that most of these particles are moving very close to the speed of light. And in this regime, a more drastic thing can happen because it's a very well-known fact about the relativistic particle physics that the particle and antiparticle can pair, create, and annihilate. So in this case, the particle number can change. Okay, as we increase the energy, there can be more particles created. But the thing is that the number of particle species is fixed. So the particle species means that electrons, muons, some quarks. The name of the particle. A given particle can be created more and more, increasing the particle number. But particle species is fixed normally in particle physics. Okay? If you look at the standard model of particle physics, there are lots of particle species, but the type of particles is fixed. Okay? So with particle species fixed, in relativistic particle physics, the entropy increases as energy increases for two reasons. Firstly, by the number of particles increasing, and their states due to this kinematic motion increasing. So naturally, the entropy in this relativistic particles case increases more faster than log. It's power in log, but it's quite small, but the power is smaller than 1, 3/4 or something. So it's still a concave growth. So if you consider these particles, they really don't ever grow fast enough. They're never convex. Okay? So this is what happens in ordinary particle physics, at least when there are no substantial interactions. Okay? But the more exotic entropic growth has been observed frequently in the quantum theory of gravity, by which I mean string theory, mostly in this text. So string theory is a grand proposal of a quantum description of gravity, and it has been well known for some while that the high energy entropy of elementary oscillating strings grows linearly as energy grows. So linear growth is not yet convex, but it's faster than concave at high energy. So this is a very well-known fact that has been observed from long ago. Okay? And the faster growth of entropy compared to all the relativistic particles can be understood as follows. Okay? So if you think about these strings oscillating in a space, different oscillation modes of a string, in a sense, represent different particle species. So that strings can oscillate in infinitely many types, meaning that the oscillation of the strings is introducing an infinite tower of particle species. So that if you increase the energy, particle species increase, the number of those particles with increased species also increase, and all the other factors contribute to make a bigger entropy growth. So that's why concave growth of the relativistic particle can change into the linear growth of the elementary strings. Okay? So there are more and more ingredients that could change as you move down. So we call this a hadron growth, and if time permits, I might be mentioning that later in this talk. This kind of linear growth in the entropy has been observed first in the hadron physics, the strong interactions of the nuclei. In the old days, people have observed many kinds of baryonic and mesonic particles or resonances. And as the energy increases, it seems that people have found new different type of particles. I mean, different type of particle species. Apparently, it seeming to lead to this kind of entropy. So Hajugan has first studied this structure in the context of strong interaction for the nucleons. And then it has been revived from 80s in the context of string theory because the structures are so similar. Okay. Yes, please.
Since you are bringing in pattern physics, I mean, although we have more number of states,
Yeah.
the fundamental constituents of those states can, I think, from the quark, that is fixed.
Yeah,
Right,
that is the right picture.
Number
Yeah,
of quarks.
yeah.
But in this case, what you are saying, in the case of quantum gravity or string theory, here you are
Yeah.
saying the states are also, I mean, unlike the case of that you have fixed number of quarks or lepton, here it is not that thing, right? In the gravity case.
Yeah, string theorists have been long thinking that this behavior could be fundamental. I've been thinking that this behavior could be fundamental until we got a deeper understanding on the string theory. And nowadays people think that perhaps the similar situation as QCD might be happening in the string. I mean, what we regarded as elementary strings might be coming from more basic and fewer ingredients. I mean, at least that idea has been tested in very well-controlled situation, which I'll try to come back later. Okay, yeah. So I'm comparing this with the early days of the nucleon theories. Okay. But still, this entropy is not growing fast enough to account for the convex growth. Means set aside the precise agreement with the black hole entropy. So the natural thing one might ask is that could there be still new objects? Could there be still new particle species other than this infinitely many of them coming from the oscillating strings? Okay. And the answer turned out to be yes from mid-90s when people got a better understanding on so-called a different kind of particle states. So if you're good at some partial differential equation, we call it solitonic states. Okay, so apart from elementary particle, there can be more complicated particles which can be appearing by some collective effects of these elementary particles and fields. Very technically, we call solitonic states, non-perturbative states, and so on. But it turns out to be new particles that can appear due to the interactions. Okay, and perhaps with the interaction with these new ingredients, you can try to form a new bound state, giving even more kind of particle species due to the interactions. Okay? And that turned out to be the case with a better understanding of the superstring theory in the mid-90s. So it is a bit, yeah. So in the 1995, the most important object called D-branes, you don't really have to know that in detail, have been discovered by Joe Polchinski, and compactifying these D-branes in the internal manifolds and so on turns out to give many extra solitonic particles on top of the particle coming from the elementary strings oscillation. So carefully studying what other particle species coming from the bound states of these non-perturbative or solitonic objects with the elementary strings, we could try to reinvestigate the questions whether the entropy growth is fast enough to account for the convexly growing entropy of black holes. Okay? So people have studied the quantum mechanical system, or more precise, very often quantum field theory system, which takes care of these bound states, and people have counted large number of states which account for the black hole entropy, accounting for the Beck-Einstein-Hawking entropy formula. For the technical reasons, we know doing this quantum mechanical calculation is often so difficult because you have to do with not so small interactions or strong correlation of these constituents. So it has been done in some exactly solvable model, which is often called extremal black hole or BPS black hole that Shiraz has introduced that I was working on. But there are some the technical jargons of that. In some exactly solvable black hole model, people have managed to do that. So in this exactly solvable black hole model, black hole carries not just mass, but also charge. And the mass of the black hole is given by the charge of the black hole. So what you want to do is to count the number of quantum states as a function of charge, which is just a mass. Okay? So these people have shown a formula like this, which gives an entropy as a quadratic function of charge, which is a convexly growing function. Okay? And that gave an expression that agrees with the Beck-Einstein-Hawking area law of the black hole entropy. The agreement was very impressive, but to me today, the more important thing is that including more and more particle species because of this new type of particles and so on, people eventually got to understand how a convexly growing entropy function can emerge by having elementary string particle species keep appearing and having even more non-perturbative solitonic particles keep appearing. Okay? And I don't know whether this is an accident or not, but if you note the fact that charge is playing the role of mass in this exactly solvable model, at least qualitatively, the growth of this function is similar to the growth of the entropy of the Schwarzschild black hole, if you recall that charge is playing the role of mass. Okay, so this is the kind of story that the first part of the story that explains that the fast-growing, convexly growing entropy has been accounted for the models of quantum gravity given by string theory by keep discovering new particle species if you increase the energy regimes. Okay? Any questions so far? Okay. So let me recap and think about what I have told you a little bit more in more detail. So I've explained to you that the fast-growing entropy is intimately related to the fundamental aspects of quantum gravity, number of new states or new particle species that they can be showing up, at least in the concrete string theory models discussed so far. And I would like to remind you that you might have heard of this in the casual introduction of the string theory, that historically people try to understand the quantum physics of gravitational physics by taking the Einstein's general relativity equation and applying the standard paradigm of particle physics to so-called quantize it. Okay? People failed because if you naively apply the standard paradigm of particle physics to general relativity, you just get theoretical inconsistency. Set aside predicting anything new. Okay? So we call this theoretical pathology ultraviolet divergences. So this has been puzzling people for some while. And the string theory has been making a drastic proposal that putting in an infinitely many extra degrees of freedom or extra particle states on top of the particles naively visible in general relativity, one can cure these technical pathologies. Okay? So that was the early motivation of why string theory should be a good thing to do to understand the quantum theory of gravity. So it was a drastic proposal, string carrying infinite number of particles, cures a technical problem. So it's a very technical motivation. Okay? But you note that the very drastic aspect, having infinitely many more particle species, played very important roles to understand the black hole entropy. So now you might get a little bit more, you might feel it a little bit more natural that these having a drastically more, infinitely more particle species would be what black hole entropy could be naturally requiring to the quantum system of gravity. Okay? So at least I became a little bit more comfortable when I realized these connections. Okay. Okay, the remaining thing I'll skip probably. So this finishes the first half of the talk. And in the remaining part, I'll keep on this idea and try to use the black hole. It will be not too long, I hope, but try to use this idea to understand the thermodynamics of gravity in a more general perspective. Okay. So motivated by this connection between the black hole entropy, black hole thermodynamics, and the event of the fundamental structure of gravity, I really now want to discuss the thermodynamics of gravity in a more general setting. Okay? For instance, I want to take a gravitational system and fix the size of it, volume, let's say, sort of. Okay? It can be very large to apply thermodynamics, but some fixed volume. Okay? And I want to see how this system behaves. As we heat this system up, cool the system down, change the temperature, see how the system behaves. I mean, I just want to understand the general thermodynamics of this system as we investigate the thermodynamics of a tank of gas. There are many subtleties appearing if you want to do this for a gravitational system. Especially, you cannot put gravity in an arbitrary box because, you know, you might have heard that gravity is a universal force, obeying the so-called equivalence principle. Any object carrying mass or energy is subject to gravitational force universally. So even the box you want to set up this question properly needs to be consistent with the structure of general relativity. So in the next slide, I'll try to explain to you very briefly what people have done to consistently put a gravity in a box. So it's a model of putting gravity in a box, and then try to better phrase lots of interesting thermodynamic questions involving black holes, of course. And as somebody in the audience might have already asked, the picture that will be unveiled after we study these thermodynamics in the extreme conditions will be very much similar to what we have seen in QCD, right? for the strong interaction. So I've explained to you that in the early days of strong interaction, people have observed power of hadrons, which once were thought of as independent particles, but we now know that they are bound states of quarks and gluons. Okay? And this bound state structure reveals most dramatically if we heat the system up. Okay? Hadrons, baryons, protons are not relevant variables, but they give way to a liberated quarks and gluons, often forming a plasma. So similar structures will try to get unveiled if we make a thought experiment of putting the gravity in a suitable consistent box and try to heat them up. That's what I'm going to try to explain to you in the remaining time. Okay? And these questions can again be theoretically studied by the window of the black hole entropy. This is the strangest slide that I prepared. I have to explain to you the name anti-de Sitter spacetime. This is the name of the box, theoretically consistent gravitational box, which can combine all the gravitational phenomena of massive particles, massive black holes into certain region. It's a strange name. It's a spacetime named against a person. So de Sitter spacetime, not anti-de Sitter, is a spacetime which is very well known to describe the accelerated expansion of our current universe. So it's a very, 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 very important spacetime. Anti-de Sitter spacetime, named against de Sitter spacetime, is having various mathematical properties against the properties enjoyed by the de Sitter spacetime. Physically, it can be explained by the following small cartoon. So I drew a cylinder. The vertical direction represents the flow of time. The horizontal spatial splice is the space. Okay? And rho means the radius of this space, meaning that a version of this anti-de Sitter space has a preferred center. And the gravitational force, I wrote down what is called a metric, but never mind. But the curved structure of this spacetime is such that the gravitational attraction acting on the massive particles by this background geometry draws the particles towards the center. Okay? If you try to move out to the boundary of this spacetime, you experience bigger and bigger forces. So it plays the role of effectively confining these massive bodies, including the black holes, towards the center of the ADS, providing some kind of traps or effective box. The length scale of this box is given by this curly L that appears and will appear everywhere in the formula. So it's roughly a box, very roughly, it's a kind of trapping box of scale, length scale L. So I'm going to study the thermodynamic physics of gravity from this setting. I think, another very critical fact that motivated the study of this setup by many quantum gravity physicists is that in this kind of particular spacetime, there is a way known to describe a full quantum gravitational system microscopically using some well-known quantum system. A fancy name of that is called the ADS-CFT correspondence, but you don't have to really remember this, why this name is given this way. It simply says that if you have this anti-de Sitter spacetime, there's a boundary, the edge of this cylinder with one less dimension. And it has been proposed, starting from this Juan Maldacena, that a certain quantum system, well-described, well-known quantum system, living on the boundary, can so-called holographically describe the gravitational phenomena inside. So we call this holographical principle, ADS-CFT correspondence. Many names are describing that. But a quantum mechanical system or quantum field theory defined that the boundary of this spacetime can secretly describe gravity inside. And we know many rules on how this works out. In simple examples, the quantum system living at the boundary is really like QCD. It consists of gluons, well, optionally quarks, but the important thing is have many, many gluons. Okay? So these gluons and quark quantum chromodynamics, like quantum field theory, the quantum system, can be used to describe the black hole and gravitational phenomena in this ADS space. So I'm going to present to you the rough picture on how both gravity people and this quantum holography people using quantum field theory could understand the thermodynamics of systems and what kind of picture that we have built out of it. Okay, so that will be what I'm going to explain to you in the remaining 10 minutes of time or so. Okay, so let me try to explain to you what kind of black holes do we have there, because black holes very often, successfully have been representing the thermodynamics of the given system. So it has been studied, the black holes in this ADS trapping box has been studied by Stephen Hawking and Don Page very long ago. And their motivation was to precisely understand the thermodynamics of gravity and black holes inside this trapped box. So that's many questions becoming better defined. So we consider for the simplicity the black hole carrying mass only, or energy only. So we call Schwarzschild black holes in ADS spacetime, antidistant spacetime. Okay. So it is a theoretical physicist taste to work on 4+1 dimensional spacetime. It's very strange. So if I have to make the plots quantitative, I happen to draw it in higher dimensional antidistant spacetime, but qualitative features go through in 4+1 dimensional trapping box, 3+1 dimensional trapping box as well. So the black holes, various properties of black holes can be investigated in this trapping box ADS. And I show to you the entropy as a function of energy, because this is my small field today. Entropy as a function of energy, or the mass, behaves in two distinctive manners, depending on whether the energy of the black hole is small or energy of the black hole is large. So energy of the black hole gets large, then the size of the black hole gets large, the radius of the black hole gets large. So when the radius of the black hole is small, black hole radius is much smaller than the size of the box, it turns out that the small black hole doesn't really feel that there exists a large box of size L. So it behaves like a black hole that I've already explained to you. Small black hole sitting in a large box is behaving like a black hole sitting in an infinite non-compact space-time. So it really becomes like the Schwarzschild black hole I explained to you before. So when the black hole size is much smaller, or energy is much smaller than the size of the box, it shows the usual, expected convex growth. So the specific heat is negative. Okay? But when the black hole grows gradually, so that it gradually feels that it's sitting in a finite sized box, then the situation changes, and the increase of the entropy tames down to a concave form. Okay? And so this black hole filling a box has a positive specific heat, showing a concave, a tamed down entropy growth. You can see this more distinctively by taking a derivative of entropy and taking inverse to plot the temperature as a function of energy. In the convex region, you see a curve between temperature and energy with a negative slope, which means that the specific heat is negative. We call this small black hole. Okay? Roughly speaking, it's the black hole which doesn't see the box, like the familiar black holes in the sky, but it has exotic thermodynamic behavior, as I explained to you. There turns out to be new branch of black holes, roughly filling the box. There are novel branch of black holes filling the box in our particular setup of a trapped gravitational system and so on. It's a novel black hole branch, but it has ordinary thermodynamics. It has a positive specific heat and so on. And if you investigate the thermodynamics of the whole system by cranking up the temperature and so on, this novel branch will determine the phase of this gravitational system when it's very hot. Okay? So people have been making studies of this both from quantum field theory and the black hole side. The quantum field theory, what we expect can be simply phrased as follows. So it's a kind of system holographically consisting of, mostly importantly, of gluons. There might be quarks in certain situations, but they're not important. And it has been, in various cases, the system described by quarks and gluons can exist in two different phases. Okay? For instance, in QCD, the QCD that we know in particle physics, is known to be in a confined phase at low temperature. Okay? So that we don't see bare quarks at low temperature. We only see the bound states of them, making protons and pions and so on. So we say this is a confinement of quarks. At high temperature, they're known to deconfine. For instance, if you collide heavy ions together at particle accelerators, they temporarily got very hot when they collide, and inside they temporarily behave like a liberated plasma of gluons and quarks. Okay, so we say that the quarks and gluons are deconfined. They expected to have some phase transition at a critical temperature, and the quarks and gluon systems that holographically describe our gravitational system are in many ways different from QCD. But this general structure of confinement and deconfinement is expected to be going through, okay? Although the mechanisms are quite different. So we expect there to be phase transition at a critical temperature set by the size of the box. We call this confinement, deconfinement phase transition. That's what you expect, roughly, from the boundary quantum field theory. Directly in the gravity side, long ago, Hawking and Page had made a study of the phase structure of this gravitational system using some semi-classical techniques. At low temperature, there turns out to be a phase which doesn't contain black hole, but populated by thermal gas of gravitons, the particle for the gravitational theory of Einstein, like photons in Maxwell theory. As you increase the temperature, there appears a phase transition, and at high temperature, there turns out to appear a new phase, the dominant new phase, governed by the presence of a large black hole, this novel black hole filling the box. Okay? So one naturally gets to a very fascinating picture that the confinement-deconfinement phase transition is holographically equivalent to the Hawking phase transition between these two configurations. And the fact that the large black holes filling the box can be described by quantum field theory by a deconfined phase of quarks and gluons. Okay? This is a beautiful story that has been established from the early days of ADS-CFT, culminating in a really important paper written by Shiraz and company in more than 20 years ago. This fascinating picture has given homeworks to many of the colleagues, okay, including myself, because when people see this nice picture, I mean, of course, they have made some consistency checks and nice qualitative tests of this beautiful picture, but we wanted to make this picture really at work, by solving some solvable models. So many people have got to that. It took surprisingly long time, 15 years after Shiraz has worked out this beautiful picture of the correspondences. There turned out to be some progress in and better understanding this phenomenon qualitatively, roughly 5 or 6 years ago. Okay? So we have again studied a solvable model. It's given by BPS black holes or extremal black holes, supersymmetric black holes, enjoying very strange theoretical symmetry. So it's a solvable model, even if the constituents are strongly interacting or strongly correlated. So we have really literally counted the states in very, I mean, technically we have to set up very, very carefully, but after all, what we have done is counted the quantum states made by the liberated gluons, okay? And the entropy obtained by counting gluons is given by the following formula, is a function of charge and angular momentum. I told you that extremal black holes has a charge playing the role of mass. In this case, charge and angular momentum, a combination of them plays the role of mass. So you get an entropy as a function of charge and angular momentum. Okay? And the formula precisely agrees with the Bekenstein-Hawking's area law, with including the coefficient. And if you look at the details, I mean, this is a formula which is especially simplified at extremely high energy. And you can really intuitively get it from counting fully liberating gluon states, but I mean, more complicated formula can be obtained, and they agree very well. And you really see, yeah. And the physics of the transition between this confining and deconfining phase, Hawking phase transition, has been also clarified from both field theory, matching what we expect from gravity. The transition, technically speaking, is a first order phase transition. It's like a transition between vapor and water at 100 degrees of Celsius. The most exciting point is that these large black holes represent a very novel phase of gravity in extreme, in sitting in an extreme phase at high temperature. Okay, so instead of describing this system like using gravitons and so on, you know, these gravitons are really holographically due to mesons and something like intrinsically. But you know that baryons and mesons are not the right variable at high temperature. Just like that, gravitons are not the right variables at the high temperature of gravity. So it should be, I don't know how to describe it properly, but it should be very extreme phase in which the traditional intuition from Einstein's general relativity not always works. Okay? So I believe it should have we believe it should have a very deep implication to the gravity generally in hot and very extreme conditions. Okay? So let me briefly conclude. I try to convey to you two messages in this rather simple talk, I believe. The first message was the intimate connection between the black hole entropy, black hole thermodynamics, and the quantum theory of gravity. Normally, the quantum theory of gravity, especially string theory, has lots of involved structures, infinitely many states and particles, so on, but they play critical role to explain the exotic entropic property of the black holes. And that makes me, at least in my mind, regard string theory as a very natural structure. I mean, explaining the thermodynamics of black holes in a natural way. Okay? So I think this develops a close connection between the fundamental structure of the quantum gravity and the thermodynamics of black holes. The second thing I'd like to emphasize is that in certain circumstances, gravity can be in extreme phases, and this can be seen from black holes. Okay. So I've been explaining to you that the gravity systems undergoes a phase transition as you increase the temperature if you confine them in a box suitably. And presumably, hopefully, they may shed some light or even predict how our universe should behave in various extreme and hot conditions. It will be very interesting to see how we can concretely implement some of our ideas or whether we can do that. So we'd like to understand this further, hopefully in the future. Okay, thank you very much. This is all.
Okay, so the talk is open for questions.
So in one of the models you discussed, that dimension was taken to be 5. So like what is the general motivation behind like choosing to study dimensions other than 3 plus 1?
It was, I believe it's a highly technical motivation to choose 4 plus 1 dimensional box, just because it's holographically corresponding to the 3 plus 1 dimensional quantum field theory, which theoretical physicists like. You can do the same kind of problem in 3 plus 1 dimensional box, for which you'll have to use some quantum field theory living in 2 plus 1 dimensions. Similar studies can be done. It's much more difficult for some technical reasons, but it can be done also. Yes.
So you gave an example where the corresponding analogy would be to a first order phase transition going through. Are there examples where you go through something like a BKT transition? In 2D superfluids, you would go through something like a Berezhinsky, Kostelis-Thouless type transition, which is neither quite the usual first order, not quite the usual second order.
I'm not exactly sure about that phase transition, but there are other kind of phase transition which can happen between different kinds of black holes and so on. This holographically realizing superconductor, superfluid, and so on.
So in this context of what you are bringing in this quark gluon plasma, the correspondence you brought in. So with the advent of high energy accelerator, now we know the quark gluon plasma is not a fixed. I mean, it's a real thing, right? It's really happening on that.
Yeah.
So the kind of thing that you just presented, I mean, now that the experimental results, I mean, earlier, as you said, black hole was a totally theoretical construct, but now that this EST collaboration and all this thing, we have taken the picture. So I'm just wondering if there is any kind of experiment, I mean, something we can sort of see the effect, maybe not exactly, so is there anything we can think about the experimental side or observational side?
Experiment from the structure of black holes.
Exactly.
Yeah. There are many things one can do indirectly. For instance, one thing that comes into my head is that, if you study these plasma of quarks and gluons, they have some particular behaviors in the viscosity to entropy ratio. And I understand some of that aspects can be understood from the gravitational physics. I mean, this viscosity ratio is somewhat similar to what the gravity is predicting, or so on. So, and that comes from the idea between the duality between these black holes and the plasma of quarks and gluons. Presumably, there might be some better examples, and hopefully better examples to come. Yeah.
So I didn't follow what you did in the last slide, but I presume what you said is that Shiraz's calculation was not for supersymmetric theories and yours is for supersymmetric theories.
The role of supersymmetric theories.
Yeah. And the fact that you got a first order transition, is that related to supersymmetry or not?
Well, we believe the thing will be general. We believe the situation will be general. I mean, supersymmetric, non-supersymmetric. The thing is that we think the general story will be. I mean, the story will be general. To carry out quantitative tests and firmly establish the picture that Shiraz has proposed, we want to make solvable analogs. I mean, we want to make studies of a solvable analog system which preserves certain supersymmetries, but yeah, just to make the quantitative calculations the strongly interacting quantum system. So I think what I've explained is not just restricted to solvable models, but I mean quantitatively illustrating with what I can compute quantitatively. Yeah. We think the picture is more general. Yeah.
Just regarding the correspondence you drew between the second law of thermodynamics
Yes. Yes.
for black holes. And so in thermodynamics, we imagine the time as like a global variable outside the theory,
What I said to say?
like a global variable which is outside the theory. Like thermodynamics does not have time embedded in it.
No.
But when we talk about the area of the event horizon, just because it is close to a singularity in space-time, is there some subtlety in how we imagine this process that the area is increasing in time, or can I just
in time? Well, thermodynamics can be done. I mean, equilibrium is just time independent, but you can do beyond that. You can have thermodynamics depending on time, right?
so when you say that the area of the black hole or the event horizon increases in time, I can just imagine it as if I'm looking at it.
Yeah,
It is
entropy
only,
increase is a fully, I mean, time dependent statement even in thermodynamics. Yeah, second law is time dependent statement. Right?
yes. So since I understand that correctly, I just wanted to understand if the black hole part is also identical to
it's
that.
the same thing. Area increases in time.
In time.
Yeah, and doesn't decrease in time. Yes. Yeah.
Any other questions? If there are none, let's thank Professor Kim again.
Thank you very much.
And we can all join him for a little bit of snacks in the left hand. Thank you very much.